All right, so we're going to review a few concepts from the Bohr model and then bridge from the Bohr model into our more modern understanding. And I'm going to begin to introduce the components of the current model of the atom. It takes 2 class periods to get through that and really get to where it starts to click and understand. So make sure that you understand that going in. As we go through the stuff today, it's kind of abstract and a little bit strange. It's different. And so bear with me because we're not really going to dig into this until your cohort classes as we go forward. So I want to remind you that at this point, you should have done the first 2 worksheets in your packet, the atomic spectra activity and also the quantum model. Sorry, not the quantum model, the Bohr model, where you fill in all those Bohr model activities, all the dots and everything. All right, you should also be preparing to take quiz 1 if you haven't already, because quiz 1 is on last week's material. I just scheduled it for this week in case anybody had any questions and wanted to ask them in class here today. All right, so this is the general view of the Bohr model where energy levels are depicted as circles, which Bohr called orbits. And you're going to see a variation on that word reappear here today in our more modern model. As we move outwards from lower energy levels to higher energy levels, then the energy or the speed at which the electron is traveling increases, right? And so that letter N is a generic letter that represents any energy level. If we don't know exactly which energy level we're talking about, we use N to substitute that. And you'll see that as we go forward a little bit. An electron would like to be in its lowest possible energy level, which is known as the ground state. That would be energy level 1 in this case, because there's only 1 electron. Remember, Bohr's model is shaped around the hydrogen atom, which only has 1 electron. It works perfectly fine for helium as well. And then starting with the 2nd energy level, the Bohr model starts to be off a little bit. And by the time we get into the 3rd energy level, it can be off by a lot. And that's what we're going to update now. So an electron, as it's depicted in this picture, is in a higher energy level. That's known as an excited state. An excited state means it's higher than its normal energy, and that comes from absorbing energy. So the electron moves out to a higher energy level when it absorbs energy. That could be from heat or electricity or from some other sources as well. Then when it has the higher energy, it can release that energy to go back to its ground state. When an electron releases its energy by slowing down or dropping to a lower energy level, then it releases a photon of light. A photon is a particle of light that has a fixed amount of energy in it. And so we can measure that energy, and then we can use that to calculate the energy of the electron inside the atom. Now with 1 electron, this was pretty simple. Bohr was able to manage it. With 2 electrons, it was quite a bit harder, but he was able to get a good approximation. The more electrons you add, the more complicated things become, and the more the Bohr model starts to fall down. However, there are a couple of things that Bohr got right and that we're going to continue to use, and you'll see them continue to come to pop up in our modern understanding of the atom and going forward into new units later on as well. Bohr determined that there are 7 energy levels in the hydrogen atom, and that is still the fundamental organizing principle that we use. There are 7 energy levels within the atom. Lower energy levels means less speed. Higher energy levels means a higher speed. And then the energy levels match the row on the periodic table. So that's an important lesson that comes out of last week. Each energy level corresponds to a period on the periodic table. So if an element is in period or row 5, it means that it has electrons in 5 energy levels, starting with the lowest. And remember how we filled out the Bohr model. We start with the lowest energy level and then work our way outwards. And that's going to continue to be true. It's just that we have found out since Bohr's model that there's a lot more detail in here. The patterns are more detailed than what Bohr described. So we need to dig a couple layers down in there and find the true pattern that's going on. And then we can use the same principle, assign electrons from the lowest energy to the highest energy. Bohr also identified the maximum number of electrons that could fit into each energy level. 2 electrons only in the 1st energy level, 8 in the 2nd, 18 in the 3rd energy level, and then 32 in the 4th. But you may remember that's not how we approached drawing the Bohr model. We didn't do 2, 8, 18. We did 2, 8, 8, and then 2, which means that we're having to adjust the Bohr model because of some discrepancies that come up. So now that's what we're going to talk about for a few minutes here. We're going to talk about what discrepancies came up that caused the Bohr model to be off, to not be correct. And then I'll show you how we're going to adjust and represent the true patterns that are going on for electrons. Remember that the goal of all of this is to understand how electrons are arranged within an atom. And the reason why we need to understand all this is because the arrangement and behavior of the electrons is going to affect them in chemical reactions. It affects the chemical properties of the atoms. And so this is the beginning of a foundation that's going to take us through 3 or 4 units before we really get to talking about chemical reactions. All right, so let me switch screens here for just a moment, and I'll show you how the Bohr model breaks down, which is also showing you a preview of the pattern, the true pattern that we're going to be following. So this is a different representation of Bohr's model. Instead of using circles, I'm just using a y-axis here. And so the y-axis represents increasing energy. So we've got energy level 1 is the lowest, and then level 2, and level 3, and level 4. And remember, the actual amounts of energy that these electrons have are different for every element. And so we don't want to use the actual amounts. We don't want to use numeric representations. I don't want to get into the numbers. Instead, we want to use a symbolic representation. We want to organize these energy levels in such a way that we can describe the arrangement of electrons without needing the numbers that represent their actual energies. Right, so energy level 1, no change here. So we're still going to consider that to be 2 electrons. Nothing has changed in that, and that's why Bohr's model works fine for hydrogen and helium, up to 2 electrons, no problems. In energy level 2, we found small discrepancies in Bohr's model. And so what I mean by that is, after Bohr developed his model, scientists refined their techniques, improved their instruments, and got more detailed measurements of the energies of electrons. So Bohr believed that all 8 of these electrons in energy level 2 were equal. He believed they were identical to each other. They would all have exactly the same energy or be traveling at exactly the same speed. He also believed they would be the same distance from the nucleus. That turned out to be false. The 8 electrons in this energy level, we now know, are not all exactly equal. They're very similar in energy, but they're not exactly equal. The 8 electrons are actually divided into 2 groups. 2 subgroups, if you would. One group has 2 electrons, and the next group has 6 electrons in it. So 2 plus 6. And I spread that out just a little bit too much because I'm going to run out of screen space up above here. That's a little bit better. Right, so instead of 8 electrons all at the same energy, we now know that there's actually a group of 2 and a group of 6. But of course, 2 plus 6 makes 8 within the energy level. And so the total number is correct. It's just that they're not all the same energy. And if we're going to put these in order from lowest energy to highest energy, we need to fill in the extra detail when Bohr's model is not 100% correct. So through energy level 2, Bohr was close, right? These are very similar in energy, but not exactly the same. But still, he had a general approximation that worked okay. It's in energy level 3 that things really start to break down here. Right, so this 18 electrons is actually divided into 3 groups. A group of 2, a group of 6, and a group of 10 electrons. When I say these groups, what I mean is electrons that have the same energy. Right, so the electrons in level 1 all have the same energy, or both of them. In level 2, the 8 electrons are divided into 2 groups. A group of 2 with the same energy, and then a group of 6 with a different energy, but the same as each other. The 18 electrons in level 3 are divided into a group of 2, a group of 6, and a group of 10. So these 10 electrons all have the same energy, which is higher than these 6 electrons that are the same as each other. And that's higher than the energy of the 2 electrons. And so these groups can actually now be ranked rather than simply ranking the energy levels. So in simple terms, Bohr had the broad picture correct, but his was too simplistic. There's a lot more detail there that he wasn't able to determine. Up here in energy level 4, I bet you can guess how we're going to start. Okay, notice the pattern, right? 2, and then 2 and 6, and then 2, 6, and 10. And so we have, and then finally, what would be left if you do the math? It's 14. So there's a repeating pattern to the arrangement of electrons inside the atom. It's just a slightly more complicated repeating pattern than what Bohr thought. And so therefore we needed the updates. You can think of it that way, Josh. That's a good question. There's actually a better way to describe the pattern, but that on the starting level, that's a good idea. I've got another layer of information for you, and then there'll be a better pattern to think of when you do that, or a better way to think about this pattern as we go forward. All right, so to summarize here, Bohr had these energy levels correct, but we now know that these energy levels are divided into smaller groups, right? So smaller groups of electrons at different energies. This one is the lowest group. These 2 electrons have the same energy and they're the lowest, right? Then the next 2 electrons are the same as each other, right, but higher than this group. And then we go up in energy again, and there's 6 electrons that have the same energy as each other, but higher than this group, and so forth and so on, right? And we can continue to measure the energies of each of these smaller groups, which we're going to call sublevels, right? And that makes sense if you think about it. We have an energy level, and then we have a sublevel, which is a part of that energy level. We have an energy level, and it's divided into sublevels. An energy level, which is divided into sublevels. And so what we need is just a way to represent these sublevels symbolically so that we can represent this repeating pattern as we go forward. And then we're going to approach it in its core the same way we approach the Bohr model. Once we know the order of the sublevels, we're simply going to fill in electrons from the lowest energy sublevel to the highest until we run out of electrons for that atom. And that's how we can describe the unique arrangement of electrons in every atom. All right, so I'll come back to this diagram in just a minute, but before we go, I want to point out something numerical about this pattern here. So remember that the energy levels correspond to the rows, right? So an element in energy level 1 is in row 1 on the periodic table, and an element whose electrons are in energy level 2 is in row 2. Right? And an element that's in row 3 would be using energy level 3, which means it could be using these sublevels. And an element in row 4 would be using 4 energy levels, which means it could be using those sublevels. Maybe not all of them, it depends on how many electrons it has in order to fill that in. This pattern repeats, by the way, so you won't see me talk about energy level 5, but level 5 is the same as level 4. In theory, there could be more sublevels, but we don't ever have any atoms with enough electrons to actually fill them, so we don't worry about them. And actually, beyond level 5, the number of sublevels that are really used in the real world decreases. So the number of sublevels actually starts to get smaller again eventually. And I want to emphasize to you that although this is going to seem a little abstract, particularly when we start learning the names that we assign to these different sublevels, these different groups of electrons, I want you to remember that this is all based on measurements of what electrons are really doing. So this is a way to describe what is really happening to the electrons inside the atom. The model is there so that we can have a generic way of looking at any element, rather than breaking down the specific energies within only one element. But just because it's generic doesn't mean that it's not specific and it's not accurate. And that's the important thing here. All of this is what we know electrons actually do. This is how electrons actually arrange themselves inside the atom. So then the question is, why? Why do atoms arrange them, or electrons arrange themselves into this repeating pattern here, right? This is real, right? This is what electrons do, and we're just trying to describe it. This is not a human created idea. This is the actual pattern in nature. right? So why do they arrange themselves into that, right? So it's not crucial for you to understand why, but I'm going to take a few minutes to explain why, and then we'll come back to the practical side of it, and that's where we'll continue to go. Electromagnetic force is the reason, but I can give you a little bit more specific information on that. But yes, David, that is the general idea. That is correct. All right, so a couple of pieces of information that will help us to understand what's going on here, right? But in the end, just know that there's a repeating pattern that you're going to have to learn. And the repeating pattern's a little complex, but it's not horrible. And it just takes a little practice and rehearsal. So that's where most of the practice in this unit comes, is after the next lesson, when we really start digging in and working with this pattern. But some people like or need to know where things come from rather than just how to do things. And so I'm going to provide that for you for a few minutes here. All right, so coming out of Bohr's failure, right? He had a success, but he also had a failure. Bohr thought he could actually map out the locations or the positions of the electrons inside the atom, which he failed to do. Coming out of that, other scientists looking at the information came to the conclusion that we may not ever be able to know the location of electrons inside the atom. What this means is that we have to choose what we're going to try to measure about an electron. And I'm going to give you an analogy. It'll seem a little weird at first, but bear with me. It actually makes sense. All right, so I want you to imagine that you go out to a highway and you're going to stand safely off to the side of the highway and watch the cars as they go past. Cars going at 65 plus miles per hour on Interstate 40, for example. So you're standing in a safe location watching cars go by on Interstate 40. There's essentially two different ways that you could record information about those cars, right? So one thing I could do is put up a couple markers and I could time the cars as they go by me. If I do that, I could calculate their speed. Or if we have a radar gun, I'm not sure if you're familiar with what that is, but it's what police use to determine the speed of cars. If you have a radar gun, you could simply point that at the cars. You can figure out how fast they're going. So I could write down this information. Car number 1 was going at this speed. Car number 2 was going at that speed. When I go back and look at that data, will that information tell me where the cars were at any given moment? If I know the speed at which the car is moving, it doesn't tell me where the car is. To stretch that analogy a little bit, imagine you're traveling to a friend's house, right? And you call your friend up to let them know you're coming, and you tell them, hey, I'm going 65 miles per hour, and then hang up, right? Well, they have no idea where you are, right? Speed doesn't tell you the location of something. And that's true about electrons. If we measure the speed of the electron, it doesn't tell us anything about where it's located inside the atom, or vice versa. So go back to the cars on the highway. As we're looking at cars on the highway, another thing that I could do is I could take pictures of the cars, right? Or I could take a video and then later on I could stop the frames on the video. If I take a highly detailed picture of the car going by with a really good camera that has a fast shutter and all the right settings, then I could get that car to freeze right there in the frame. And I can have a clear picture of a car that was driving past me on the highway. But when I go back and look at that picture, will there be any indication how fast it's moving? So I get a snapshot, a moment in time, a split second where I know exactly where the car was located, but then that freeze frame, that still image doesn't tell me anything about how fast the car is moving. Right? And so I need to do both of those things if I want to know the speed and position. I have one instrument that can measure the position of a car, which is a camera. I have another instrument that can measure the speed of the car, which I could do with a stopwatch or a radar gun. But I can't get both pieces of information from any one instrument. Now, when it comes to electrons, it's even harder, right? So first of all, electrons are very small. There is no such thing as a camera that we can put in the atom and take a snapshot of where the electrons are located, right? We can measure their light that they produce, as you saw in the activity that you watched. And so by measuring their light, we can calculate their speeds. That's like timing cars as they go past you so that you calculate their speeds. Since that's the only thing that we can directly measure about the electron, and that tells us about the speed of the electron. It means we can never really know for sure the location of an electron inside the atom. We don't have a way to. We don't have an instrument that we can use to directly measure the location or the position of the electron. The only thing we can directly measure is its energy. And so we don't know for sure where the electrons are inside the atom. So then another scientist, Schrödinger, had an interesting idea here. And you may have heard of Schrödinger. He's memeable and shows up in memes occasionally if you're paying attention, mostly geek and science memes, but still, Schrödinger's cat is a famous example. And he dealt with probability. Schrödinger was actually a mathematician, not as much a scientist. He dealt with probability. And that's what the Schrödinger's cat example is. And that's not really relevant to what we're talking about right here today. But if we cannot know for sure where electrons are located, then maybe it would be better to use probability to calculate where electrons might be located inside the atom. And so that was Schrödinger's approach. He used complex probability equations to try to determine the most likely locations. And what he wanted to do was explain those groups that I showed you. Why do electrons show up in groups of 2, 6, 10, and 14 inside the atom? And what he found was that the empty space inside the atom, remember, electrons are flying around in what's supposed to be all this empty space. What he found is that based on the forces, which David mentioned, electromagnetic forces that are acting on the electron inside the atom, the empty space is actually divided into regions where electrons are much more likely to be. So there's a lot of empty space where electrons are not likely to be. And then there are defined shapes, three-dimensional shapes within the atom where the electrons are likely to be based on their energies. And so that's why the groups have the sizes that they do. It's because the forces acting on the electrons create regions of empty space of certain sizes, and that therefore can hold certain amounts of electrons, or there can be a certain amount of electrons inside that space. We don't know where, but we just know the electron's in there somewhere. Okay? And so that's what Schrödinger did to update the Bohr model and lead us into what we call the quantum model of the atom. He figured out all of these different spaces that can hold electrons that have different shapes, and they're grouped together. And he explained, therefore, why we have these groups of 2, 6, 10, and 14 inside the atom. So electrons do not all follow a fixed orbit. They're not all at the same distance away from the nucleus in their energy levels. They're not even all the same energy in their energy levels. The energy levels are now going to be broken down into sublevels. And then those sublevels correspond to specific regions, areas of space inside the atom where electrons are likely to be located. Now, if all that mostly flew over your head, it's okay. First of all, a lot more of this will click when we work and actually put our hands on this in your cohort class. But secondly, it's not crucial to understand the background for all of this. But it does lead us to an important term. Schrödinger called these areas of space, these different shapes where electrons are likely to be found, he called them orbitals. So it's kind of like a nod to Bohr's model. It's like paying homage to what Bohr said. Orbits wasn't right, so we're going to change the word, and we called it orbitals. An orbital is a region of space inside the atom where electrons are very likely to be found, where there's a high probability of electrons existing. And Schrödinger found different spaces of different sizes, which is what accounts for the different groups of electrons. What he also found is that there's never any space that can hold any less than 2 electrons. And so, in fact, all of these spaces that he found could hold a pair of electrons. So what he found is that electrons tend to be paired within the atom, which was a little surprising because remember, electrons are negatively charged and they should want to repel each other and move away from each other. But yet, we can find electrons paired up in relatively small spaces inside the atom. And so that needed more explanation as well. So an orbital is a region of space, a defined space inside the atom that can hold up to 2 electrons. Right? When the electrons are in the same orbital, they have to spin in opposite directions. Now I'm going to pass on that statement right now, and we're going to come back to it and examine it more tomorrow because it has some implications for what we're doing. Well, not tomorrow for some of you, in your cohort classes. So each orbital is assigned to a sublevel, and the sublevel is a part of the energy level. So we've broken our energy levels down into 2 layers of detail, right? So what used to be a full energy level is now divided into sublevels, and then sublevels have orbitals inside them. It's kind of like you have a shelf, right? And then on the shelf, you're going to put a container, and then inside the container, there's boxes where things can be held. We've got these, that's the structure that we use to describe the arrangement of electrons. Orbitals are the smallest, and they can hold 2 electrons. And then orbitals fit within sublevels, which have different sizes. And then sublevels fit within the energy levels. Right? And that's what we're going to work with. And so all we need to do now is name the orbitals, give them a symbol that represents them, and then put them in order. Right? And that's what we're going to talk about here today. We're going to name the orbitals, and then tomorrow we're going to talk about putting them in order. Right? So the orbitals can be arranged from lowest to highest energy. And when Schrodinger did all this, there were a lot of factors that he included in his probability calculations. These were very complex calculations that he did. He calculated based on things like the distance away from the nucleus, the size and shape of the space, the distance to other electrons, and then of course it's all based on fundamentally the speed at which the electrons are traveling. And then taking all those factors into account, he calculated these different probabilities. Right, so let me go back to my other screen for a moment. All right, and let's talk about how we're going to address this. So notice that this repeating pattern, right? We're going to assign each of those names. That's what Schrodinger did. He gave a name to each of these, right? That name was originally a word. Now those words have been lost and letters are used to represent these. So each of these sublevels, right? The 2s, the 6s, the 10s, and the 14s, they have a letter that's associated with them so that we can have a generic way to represent these for any atom. Right, so a group of 2 electrons is assigned the name or the letter S. Right, so this is an S sublevel. It's part of a larger energy level, and so it's a group within a larger group, so to speak. Right, within an energy level, there can be sublevels, and this sublevel that has 2 electrons in it is called S. Don't ask me where these letters come from because the words that they're based on are largely lost. I believe I know where that one comes from, but I don't know the others. They were probably written in German anyway. Schrodinger was German and wrote his work in German. All right, so going on, the group of 6 is assigned the letter P. Right, so any group of 6 is assigned the letter P. The group of 10 is assigned the letter D. And a group of 14 is given the letter F. And again, this pattern repeats itself if you go to higher energy levels. So level 5 also has an S, a P, a D, and an F. We'll break these down in a minute. Okay? Now, how do I tell the difference between this S sublevel and all these other S's, or between this P and that P, or between this D and that D? And so what we also need to do is include the energy level when we name these, because there are more than one S sublevel inside an atom. There can be more than one P sublevel inside an atom. So we need to rank these according to their energy. So this is the lowest S sublevel. It's in energy level 1. So we're going to call it 1S. This S sublevel is in level 2, so we call that 2S. And this is in level 3, so we call it 3S. And this is in level 4. Right, and so this is how we're going to name every sublevel inside the atom that can hold electrons. We name them by the energy level they're in, and then the size and shape, which is what determines the number of electrons that are in them. And so an orbital of this size and shape is given the symbol S. This is the 1S sublevel, 2S sublevel, 3S sublevel, and so on. Same thing for P. Notice there is no 1P because there's not enough electrons. There's not enough space there for there to be a P sublevel. So 2P, right? This would be 3P. and that would be 4p, and so on. There could be a 5p and a 6p as well. This is the first D sublevel. It's in energy level 3. It's the 3D sublevel, and this is 4D. And then finally, this would be 4F up here. And all we need to do once these are named is then put them in the correct order from lowest energy to highest energy, right? Which actually brought one more complication. So you didn't think we were going to get away without having at least one more difficulty in this process. And we'll talk about that later on this week. But this is our system. This is the system that Schrodinger developed, and this is what's known as the quantum mechanical model of the atom. Sublevels given a name by their energy level and type of sublevel that they have. Okay, so this is the basis for the new pattern that we're going to look at. Now you can see Bohr's model was much simpler, which is the problem. The arrangement of electrons is not simple inside the atom. Once we get accurate measurements of the electron energies, they follow a complex pattern. Electrons are actually quite complicated. So level 1, level 2, level 3, level 4 was not enough. We have to divide it into smaller details. 1s, 2s, 2p, 3s, 3p, and so on. Right? And then we're going to put those into the correct order, and then it'll simply be a repeating pattern that we can follow, and we'll assign electrons from the lowest sublevel to the highest sublevel, just the way we assigned electrons from inside to outside on the Bohr model. All right, so let's finish up our discussion here. And again, what I'm doing is sharing with you the information that is part of our pattern. So I'm introducing all the terms, the letters, the numbers that you're going to see, and then tomorrow or in your cohort classes, we will dig into the actual way this works. You'll start solving, you'll start seeing how the patterns work and rehearsing and repeating, and then things will begin to click better. All right, so there are 4 kinds of sublevels, and in theory, there could be more kinds of sublevels, but no atoms actually use those. And so we don't worry about describing them. In other words, there's more spaces inside the atom than there are electrons to fill them, even in the largest atoms. All right, so the 4 kinds of sublevel that we're talking about, the first sublevel is called an S sublevel, and it is simply a single orbital. It is one space in which 2 electrons can be. So the key rule to remember all the way through this is that an orbital can hold up to 2 electrons, and the orbital is the fundamental unit of our pattern. The orbital is where the electrons are actually going to be assigned as we go forward. And orbitals are grouped into sublevels, and then sublevels make up the energy levels. And so that's what we're going to do. We're going to break it all the way down to the lowest level and then build them back up again to get the total picture of what we're doing. So an S sublevel just has one orbital. That's all it is. It's a single orbital, which means only 2 electrons can be in it. The second kind of sublevel is called P, right? It is a group of 6 electrons. Now, if each orbital can hold 2 electrons, that means there's 3 orbitals in there. So an S sublevel has only 1 orbital, but a P sublevel has 3 orbitals. Now remember, not only was Schrodinger detailing the pattern of the electrons, but he was also describing the shapes of these orbitals. I'm going to show you the shapes, but you need to understand that you do not have to know this. I'm not going to quiz you on the shapes of these orbitals, because at the end of all this, we come out with a repeating pattern that we use, and all you have to be able to do is to follow that repeating pattern. All right, so S sublevel holds 1 orbital, P sublevel has 3 orbitals. All right, so an S sublevel looks exactly like Bohr's energy shells. Right, remember, although we drew Bohr's energy levels as circles, they were actually spheres because the atom is 3-dimensional. It's not flat. So Bohr believed that electrons would be in these spheres orbiting around the nucleus. Well, it's not quite right, but at least one sublevel looks that way. The other sublevels don't, but at least there's something that's similar to Bohr's model in here. Right, so an S sublevel is spherical, which is where I believe the letter S comes from originally. It's a spherical orbital, and 2 electrons, however, can be flying around anywhere in that sphere. So they're not right on the edge of it, orbiting neatly in a predictable pattern. The electrons can be flying anywhere within that sphere. The S sublevel, or the sphere for level 1, would be very small. The S sublevel for level 2 would be bigger, and for level 3 would be bigger. And so these are concentric spheres. And so the S sublevels are exactly what Bohr thought the electrons were going to be like in the atom. But what he thought turns out to only be a small part of the total picture. P sublevels are arranged three-dimensionally like this, right? Each orbital in a P sublevel looks like a dumbbell. It's got two lobes that stick out on different sides of an axis. Now you might notice this is a three-dimensional graph, so it has X, Y, and Z axis. If you haven't done three-dimensional graphs in your math classes, don't worry about it. Don't freak out too much. But all we're saying is that Schrödinger found that in order for there to be three orbitals arranged around the nucleus, which is at the origin of the axes here, they had to have this shape, one on each axis. I have a different picture of that I'll show you later on. And again, you don't have to know these shapes. I just think they're interesting. All right, so S has one orbital, P has three orbitals. All right, so then a pattern is beginning to establish. And Josh, this is the better pattern that we talked about earlier, right? D sublevel has 5 orbitals in it, which gives us a total of 10 electrons, right? And so 5 orbitals means 5 different spaces that can hold 2 electrons. And that gives us a total of 10. And then finally, the F sublevel has 7 orbitals. So it's 1, 3, 5, 7. So the number of orbitals increase by odd numbers as we go through this. There's a lot of numeric patterns in here, but you don't have to actually use those numeric patterns. All we need to know is the symbolic one, and you'll see what I mean as we go through this. But if you really want to dig deeply into it, there's a lot of mathematical patterns in here that we don't need, but are interesting sometimes and can help us understand things. Right, so a D sublevel has 5 orbitals, which can hold a total of 10 electrons. An F sublevel has 7 orbitals, which can hold a total of 14 electrons. If there was going to be a 5th kind of sublevel, right, then it would have 9 orbitals. It could hold a total of 18 electrons. But there's no atom that we know of that has enough electrons to actually use one of those. So we don't describe those. We only describe 4 types of sublevels because those are the only types of sublevels that are actually used by electrons inside the atom. Now, if you care, this is what a D orbital, a single D orbital looks like this. It has 4 lobes, and the 2 electrons could be anywhere in those 4 lobes. And this is what a single F orbital looks like. It has 8 lobes, and again, 2 electrons could be anywhere within those 8 lobes. All right, so getting back to the practical stuff here. I mentioned this last week, but reviewing it again, all right? Every energy level is assigned a number, and if you want to look into these deeper, there's an optional unit at the end of this unit. 5.5 is the optional challenge unit, and it digs into the idea of quantum numbers because, again, there are mathematical patterns to these that we're not really going into. The principal quantum number tells me the energy level of the electron, right? And those are Bohr's energy levels. And then within that energy level, we divide into sublevel. And then within that sublevel, we look at orbitals. Right? Now I'm going to have a visual way to represent this, but obviously this is a lot more complex than Bohr's model. So we can't just draw circles and put electrons in them. It's going to take a more sophisticated system to do that. Right? So breaking down each energy level again, energy level 1 has room for 1 sublevel, right? And then that would be S. So in energy level 1, there's only 1 sublevel, that's sublevel S. And sublevel S only has 1 orbital, right? So the whole of the first energy level is just a single orbital that can hold up to 2 electrons. Energy level 2 has 2 sublevels. There's another mathematical pattern, by the way. The energy level, or the principal quantum number, tells you how many sublevels there can be. So level 1 has 1 sublevel, level 2 has 2 sublevels, level 3 has 3 sublevels. Okay, so there's a lot of ways to look at these and learn these patterns, and whatever clicks with you, then that's great. But in the end, it's just about learning the pattern. So energy level 2 has two sublevels, S and P. And the reason why they're always assigned in this order is because those are the lowest energy. S has the lowest energy, and then P is the next lowest, and then D, and then F. And so we're always having to progress from the lowest energy possible option up to higher energy options. All right, so S has one orbital, P has three orbitals. So that means in energy level 2, there's a total of 4 orbitals. 4 holding 2 electrons makes a total of 8, just like Bohr said. So Bohr had the totals right. He just didn't have all the detail about the electrons inside those totals. Energy level 3 has 3 sublevels. So that would be S, P, and D, right? 3S, 3P, and 3D. Again, going from lowest energy to highest energy. And the reason why the D is higher energy than the P is simply because there's more electrons in it, and electrons repel each other, and that force of repulsion adds energy to their movement. Again, not important, but if you like the explanation. D sublevels have 5 orbitals, so S is 1, P is 3, D is 5. 1 plus 3 plus 5 gives us a total of 9 orbitals. Every orbital can hold up to 2 electrons, so that means a maximum of 18, just like Bohr said. And then finally, level 4 has 4 sublevels. So 4s, 4p, 4d, and 4f. 1 orbital, 3 orbitals, 5 orbitals, and 7 orbitals, which adds up to a total of 16. 16 spaces that can hold 2 electrons, and that makes a total of 32 electrons. Right? So that is the accurate information about how electrons can be arranged inside the atom. These reflect what is actually going on in there and reflect our best measurements and our best understandings of the behavior of electrons. And then what's coming up is simply our way of arranging these into a pattern that we can use, a shorthand that we can use to describe the arrangement of electron for any element. And remember, every element has a unique arrangement, so we need a system that will provide a unique description of every element's arrangement. And that's what we're going to do. That's where these 4s and 3p and etc., that's where all these will come in tomorrow.